scraping your knee, having a tooth pulled, coming down with strep throat. All are painful yet common conditions. Fortunately, treatment with antibiotics allows us to get back to normal life within a few days. Before the discovery of antibiotics, however, life was much more fragile. A trivial injury or a minor medical procedure could lead to a serious infection or even death. The discovery of penicillin paved the way to fight infectious diseases, and today antibiotics are an important component in the toolbox of modern medicine. The Centers for Disease Control estimates that 4 out of 5 Americans are prescribed antibiotics, and over 30 million pounds of antibiotics are used to treat livestock each year. Soon after the introduction of antibiotics, it was discovered that bacteria could become resistant to the action of antibiotics through spontaneous mutations. Overuse of antibiotics has caused alarming levels of antibiotic resistance, as well as the appearance of superbugs, strains of bacteria that are resistant to all known antibiotics. In the United States alone, each year at least 2 million people acquire serious infections caused by bacteria that are resistant to one or more of the antibiotics designed to treat those infections. Antibiotic-resistant infections are the direct cause of over 700,000 deaths worldwide, and without successful efforts to curb antibiotic resistance or the development of new drugs, the number of deaths per year is expected to balloon to 10 million by 2050. Deaths due to infection by resistant bacteria will exceed the 8.2 million lives currently lost to cancer each year. Because of this, researchers are urgently seeking to develop novel antibiotics.
Our approach to combat antibiotic resistance relies on taking active antibiotics that are not currently heavily used in the clinic and modify them using the tools of organic chemistry with the hope of retaining their activity while making them less susceptible to resistance mechanisms. We are focusing on aminoglycoside antibiotics, a large family of naturally occurring antibacterial agents, which are very potent, but are not being heavily used because of their side effects, as well as because of the persistence of various resistance mechanisms. Aminoglycoside antibiotics are known to interact primarily with the bacterial ribosome, the machine that makes proteins in bacteria, and interfere with the fidelity of the process. As a result, the bacteria make errors in the proteins that it produces and eventually dies. The approach we're taking to combat resistance chemically is to try and retain the elements that are essential for antibacterial activity while introducing modifications that lower the affinity to the resistance-causing enzymes. We're using the basic tools of synthetic organic chemistry in which we selectively activate a hydroxyl group towards an SN2 reaction, which allows us then to introduce multiple modifications through a substitution reaction, which then allows us or facilitates the preparation of a variety or a library of different compounds, which we can then screen for potential activity.
Chemical reactions proceed through a variety of mechanisms. One in particular that you see very often is the SN2 mechanism. So what does this actually mean? The SN2 mechanism is easier to understand if you think about it backwards. So it's a second-order nucleophilic substitution. And what exactly does that mean? So a substitution means that one group is replacing another. In our case, in this mechanism, that group is the nucleophile. And what that means is that it uses a lone pair to do the chemistry that actually replaces the leaving group. And lastly, this reaction proceeds through a second-order mechanism, and that means that it is dependent on both the substrate as well as the nucleophile concentrations when talking about the rate law. So now, let's think about this in a generic sense, where we have a substrate with a leaving group. We treat that with a nucleophile. Chemistry happens, and we have replacement of the leaving group with the nucleophile. So what we were talking about with the second order means that this reaction rate depends both on the leaving group substrate concentration as well as the nucleophile concentration. So let's talk a little bit more about what that actually means. So now if we're going to look at the rate as a function of substrate concentration, holding the nucleophile concentration constant, what we'll see is that with increasing concentration, we actually get an increasing rate. Similarly, if we look at the rate when varying the nucleophile concentration and leaving the substrate concentration constant, we will see a similar increase in rate trend. So if we actually write the rate law for this, what we would get is that the rate is equal to the rate constant times the concentration of the substrate and the nucleophile. So let's take a little closer look at this reaction here. What you see is that the substrate actually underwent an inversion of stereochemistry upon reacting with the nucleophile. This has actually been shown experimentally for all SN2 reactions. So this fact, along with the second order rate law that we spoke about previously, gives us grounds to propose a mechanism as well as a transition state. I'm going to draw this molecule in a little bit different conformation so we can look at how this reaction actually happens. So the nucleophile attacks from the backside, and simultaneously the leaving group will leave. This is what gives us that inversion of stereochemistry. And what you can actually see is that because these two things are happening simultaneously, that's why the rate law is second order. The rate limiting step is dependent on both substrate and nucleophile. So now what we can look at a little more closely is what the transition state actually looks like. So when this molecule is undergoing this transformation, we go through an intermediate that looks like this, where we have the leaving group bond breaking while the nucleophile bond to the carbon is actually forming. And you can see that the nucleophile started as a minus, it still has a delta minus. The leaving group is leaving with its electrons, forming a delta minus, and at the carbon, you actually have a delta plus. So this transition state explains, well, transition state as well as the mechanism, it explains the second order rate law and gives us an explanation for why it's an inversion of stereochemistry. And what you'll see is that the product looks similar to the starting material, except for we do have an inversion at that carbon center. So why does that happen this way? Why do we not have retention of stereochemistry or a scrambling of stereochemistry? The reason is explained when you look at the bonding and antibonding orbitals of this group. So we have a bonding orbital here between the leaving group and the carbon, and you see the bonding orbital is between the two groups. Now if we look at the antibonding orbital between the carbon and leaving group, which should be empty, we have something that looks more like this. So when the nucleophile attacks, it cannot place that lone pair into an orbital that's already full. So it needs to find an empty orbital. This empty orbital that it takes advantage of is actually the antibonding orbital of the carbon leaving group bond. So the nucleophile attacks from the backside at the antibonding orbital, pushes out the leaving group, and forms a new bond opposite where the leaving group was. And this is why we have our second order inversion of stereochemistry mechanism. So what actually affects the reactivity during an SN2 mechanism? One major factor is the steric bulk, both of the nucleophile as well as the electrophile. This is because when the nucleophile attacks the electrophile from the backside, it's going to be experiencing a lot of steric bulk because it has to get really close to the carbon in order to access that antibonding orbital. So if you compare two nucleophiles, we have methanol here and T-butyl alcohol here. you can see that by adding the steric bulk on the carbon bearing the nucleophilic atom, that you're going to greatly decrease the ability of the nucleophile to get into proximity with that antibonding orbital. Similarly, the electrophile, which bears the antibonding orbital, the sterics of it will greatly affect the same ability. So let's look at here, going from a tertiary bromide all the way down to a methyl bromide, we can compare the rates of reaction. Here, there's essentially no reaction. The rate is so slow that we say it's essentially non-reactive. And as you go from secondary to primary to tertiary, or to methyl bromide, you see that we actually get a 1,000-fold increase in rate. So from what we've just shown, we can see that the sterics of the reactive partners greatly affect the reactivity, and in other words, the reaction rate. So another factor that affects the reactivity is the actual identity of the nucleophile and electrophile. So let's look at the nucleophile first. What we actually see is that there's a trend on the periodic table. So going down a column, we increase nucleophilicity. This is because the polarizability of the atom actually increases. And then we also increase nucleophilicity going to the left. This is because electronegativity decreases going toward the left. It's important to note here that even though we are showing you these charged nucleophiles, neutral nucleophiles follow the same trend. Another important note is that these neutral nucleophiles will always be less nucleophilic than their charged counterpart. So for instance, HF is always going to be less nucleophilic than fluorine. Water is less nucleophilic than OH minus, and ammonia is less nucleophilic than the amide counterpart. So now that we've talked about the nucleophile, let's think about the electrophile. Really here, it's the identity of the leaving group on the electrophile. So in general, what makes a good leaving group is that it's stable after it leaves. Because of that, a good way to think about them is that if we follow the trend of acidity, meaning that the stronger the acid, the more stable the conjugate base, we can determine that the more stable leaving groups will actually be the conjugate bases of strong acids. So for instance, HI and HCl, the conjugate bases are fairly polarizable, and so they're actually fairly good leaving groups. When we get down to something like tosylate, we actually have resonance stability in the conjugate base, which is also a sign of a good leaving group. So in general, when you're thinking about the stability of a leaving group, what you can see is that the acidity increases along with the stability of the leaving group. So here, this is where we actually looked into the reactivity based on the identity of the nucleophile and the electrophile. Now that we've seen that not all leaving groups are the same, let's look at an example. Say that we have ethanol, and we want to displace this alcohol group. So if we have our nucleophile here coming in to attack, what we're left with now is our desired product and hydroxide. But let's revisit the concept we just learned. Hydroxide is the conjugate base of a weak acid, and therefore it's not a very good leaving group. And a better leaving group would be water, which is neutral, and it is the conjugate base of a strong acid, which is hydronium. So what we can do is activate this alcohol by protonating it. So the lone pair on the alcohol picks up a hydrogen, and now what we have is a protonated alcohol that's positively charged. So now our nucleophile can come in and displace the leaving group, which we have changed to be water. So this can be done for nucleophiles other than oxygen, and it can be done in different ways. Here we use protonation in order to activate our nucleophile, or our electrophile, sorry, but what we can also use is alkylation. So say that we have a sulfur with 3 alkyl groups on it. Now, when our nucleophile comes in, to displace the sulfur, we are left with two neutral species, both of which are stable. So even if your reaction involves a leaving group that's not ideal, there are ways to make it a better leaving group by activating it. Now that we've talked all about the SN2 mechanism and the reactive partners, let's talk about an example that's biologically relevant. Your body and other living systems produce something called SAM, which is S-adenosylmethionine. It's an alkylating agent, specifically a methylating agent, where it utilizes this activated sulfur electrophile to transfer a methyl group onto the nucleophile of different biological molecules. In this case, we're going to talk about the conversion of noradrenaline to adrenaline. Noradrenaline has this free amine group that gets methylated to form adrenaline. So we're going to get a little more basic here in our structures, just to write out the mechanism. So you can see here that we have our activated methyl electrophile. The nitrogen of the noradrenaline will come in and attack the carbon, kicking out this neutral sulfur group. Now, if this sulfur wasn't activated or didn't have this positive charge, it wouldn't be such a stable leaving group, and this reaction would not proceed quite so easily. But what we see here is that we actually have two neutral products from our reaction. Now, it's good to note that SAM is not exclusive for this reaction. It's actually used to methylate a plethora of different biological molecules, and not only in humans. For instance, bacterial antibiotic resistance, one mechanism through which that happens is through the methylation of the RNA in the bacteria, which is really important because by knowing this, we can actually use that tool or that knowledge to alter the antibiotics to try to fight this resistance. So now let's look at how we can use the SN2 reaction mechanism to combat antibiotic resistance. The TOR group is modifying a class of antibiotics called AMINOGLYCOSIDES. They're doing so in a manner so as not to perturb the interaction in the bacteria so much that we lose activity, but just enough to overcome this resistance. The location they chose to modify in order to achieve this is the primary alcohol. In order to modify this location, we have to do an SN2 reaction. However, as you can see, the aminoglycoside is covered in nucleophiles. And if we want to substitute the alcohol, then we need to block those nucleophiles. Nitrogen, like we learned earlier, is a much better nucleophile than oxygen, so those are the ones we really have to worry about. So what we'll first start by doing is actually blocking the nitrogen so that they're no longer nucleophilic. After we've done that, now we need to activate our electrophile. So as you see here, and as we talked about earlier, OH- is not a good leaving group. So in order to selectively modify that location, we should make it into a better leaving group. And we want to activate it. And actually, its natural properties, being that it's a primary alcohol and all of the other alcohols are secondary, allows us to activate it selectively using a very bulky activating group, which we call TIPS. So once this alcohol is activated using TIPS, then we can selectively substitute it with any nucleophile of our choice, creating a library of different aminoglycosides that we can then test the activity of. So in order to get back to our ready-to-go aminoglycoside molecule, the last thing we need to do is deprotect the nitrogens and remove that blocking group. So here you see we've substituted our alcohol and removed the nitrogens, and we're ready to go. We've looked at just now how bacteria actually create resistance toward antibiotics using the SN2 mechanism, and how now, as chemists, we can actually combat that also through the SN2 mechanism. So this has been a quick tutorial on the basics of the SN2 mechanism and how it's biologically relevant as well as synthetically relevant. I hope you've enjoyed it, I hope you've learned something, and I'll see you next time.